Good afternoon, everyone. My name is Jacob Rubi. This is Dylan Huval and Dylan Oslet. And today we're going to be talking about our friction stir forward extrusion process and design that we worked with Dr. Emblem on this semester. Today I'll go over a brief overview of what we'll be discussing today. Our project background, including what is the process and what is friction stir, our goals and purposes for our project, and the end products and deliverables as set by Dr. Emblem here. The timeline of events and our major accomplishments, the financial review and the budget, and we had a $500 budget set and we were able to maintain that, and we'll discuss further on how we did on that. Then we'll go into our technical approach, which will include our final design and our results from that and our test data. Finally, we'll go into our observations and our future research plans for the university.
So basically, what is friction stir? Our project is loosely based off of friction stir welding, in which a probe makes contact with two metal blocks, and as it makes contact, it spins, creating heat generated from friction. The friction stirs the grain size, and then when it moves in a longitudinal direction, it welds the two materials together, thus creating a smaller grain size and making better properties, such as ductility, tensile strength, and maybe even conductivity. There are two types of friction stir extrusion. One is forward, in which you produce solid wires. The key to this process is the hollow probe, as you can see on that top picture. The probe spins and makes contact with the workpiece right there. As it makes contact, it generates friction, softens the material, and with a downward pressing motion, it extrudes the metal up into the probe. The second type of friction stir extrusion is reverse extrusion, in which you're creating a hollow tube. This time the probe is solid, makes contact with the workpiece, generates friction, and it forms the workpiece around the probe. Instead of making a solid block, it makes a hollow tube. Goals and purposes, as said by Dr. Emblem, we were told to design a process and manufacture the tooling. What we also did was we used the thermocouple data for acquisition purposes. We recorded the effects of the probe speed on the temperature of the workpieces. We are also analyzing the differences in the grain structure between the samples using microscopy and SEM analysis. And we stayed within the budget of $500, as I'll talk about shortly. What we're delivering to you, we have our manufactured dies and probes and our inserts. We have successfully designed a repeatable process that can produce successful samples. And we have produced 11 successful samples of the aluminum 1100 series. We were told to produce samples of 3/8 inch, 1/4 inch, 1/8 inch, and 1/16 inch. We successfully produced 3/8 inch and 1/4 inch, and we're still working on the other two. We successfully acquired temperature data through the use of the thermocouple. And we, in the process of observing material properties of the test samples using microscopy and SEM. Here's our Gantt chart. As you can see, we're fully where we're supposed to be at. One key hassle that we had was the manufacturing. That took longer than expected, mostly because we were trying to find a suitable donor to manufacture the material, because H13 is rather expensive to manufacture with. Thankfully, we had Zach's husband. He offered to produce our die halves for free. Here is our cost analysis. As you can see, we have our remaining $56 left, and so we're under budget. Our most expensive aspect were just purchasing the two die halves. The H13 steel, which is rather expensive. Second most expensive are our two for our probes, the material for our probes. Fortunately, we were able to manufacture the probe ourselves. We just had to buy the material. All right. Now I'll lead you into our technical approach, where we'll discuss our specification sheet, our final design, analysis of the design, the manufacturing of the product, our testing procedure, and our results. Dylan Huval will continue on from here.
Right, so I was the manufacturing and testing lead, and I'm going to go over the specification sheet first. It just kind of goes over the different parts of the design that we need to meet, and it can help us keep track of different parts of the design that we ended up with. So for example, like we had to withstand, material properties had to withstand like 1500 degrees Fahrenheit, which is pretty high. We didn't expect it to get that high, but we wanted to make sure it would withstand that. We used aluminum alloy, 1100 workpieces that were 1.5 inches long. We use that in every test. Just kind of helped us keep track of different things. So for our final design, we went with a split die design. It's got two separate die halves that are held together with some 1/2 inch bolts and hardware, and it has removable inserts that allow us to, the inserts take a lot of the heat and frictional forces and wear, so we don't put a lot of strain on those bigger die halves. Here you can see the SolidWorks models that we created. You can see on the right side is a cross section with the probe, so you can see how the probe is hollow, and it's got an extrusion hole and then a relief hole so that the wire doesn't have to be stuck in the probe the whole way. This also is necessary for manufacturing purposes. The main die halves are made out of H13 mold steel, and the inserts made out of D2 steel. And the probes are also made out of D2 drill rod. So in order to make sure that the probes will withstand the forces that we were expecting for the in the process, we developed an FBA model of for stress. We used SolidWorks, and we imported the models into the FBA Analysis simulation part of SolidWorks. We applied the fixtures, which represent where the probe is attached to the chuck, and we applied a torque and an axial force at the end. We just assumed 100 pounds axial force and 252 foot-pounds of torque on the face, and using that equation right there. And we assumed that because the mill is 2 horsepower, and we weren't going to go anywhere under 500 RPM, so that's the maximum possible torque that would be experienced by the probe. And we did that just to make sure there's no chance of it under ideal conditions. Another part of the design that we had to develop was a thermocouple measurement system. We used an Arduino Red board accompanied by 2 Type J thermocouples. They were both attached to a max amplifier from Adafruit. We used the code that was supplied by Adafruit to incorporate it into the Arduino code, but we modified it so that it would report both values at the same instance. And it also records the time. And in order to read and interpret what those values are giving us, so the thermocouples aren't inserted directly where we want to measure the temperature. So we created an FBA model, a transient thermal heat model in SolidWorks to kind of estimate what those temperatures are. This isn't entirely accurate. There's a lot of assumptions made here, but it gives us a pretty good idea of how the temperature flows throughout the part. So now, next I'll talk about manufacturing. So like we said, we had Zach here help us with the manufacturing part of our design. We had got some quotes from local machine shops, and it was way out of our budget. So we took the step and we ordered the material and got it made ourselves. You just see the 2 counterparts right after machining. And you can see now they're pretty much the same. They withstand the friction of it, but it created a lot of heat, and there's like thermal residual wear on there. A couple, like I said, issues of cost, and if we would have went with another machine shop, it would have taken up to 2 or 3 weeks, which we really didn't have time. Another problem we ran into when we were manufacturing the probes was we tried to use an 1/8 inch drill bit, cobalt drill bit, which is designed for cutting really high strength material. And every time we tried it, it would break off inside the probe. So we figured whenever we tried the 1/16, it would do the same thing, so we didn't attempt to make 1/16 probe. A couple ways you can get around that is to use a different manufacturing process. You can use EDM or possibly water jet to create these probes, but we just didn't have access to those machines. And we also broke a drill bit in one of those die half. I'll go over the test procedure as well. So first thing first, we had to make sure it was safe. We wore safety glasses in every test, and since there's a lot of heat involved, we use gloves. We set the mill up. First, we put the probe in a collet chuck, and we insert that into the mill. And then we put the assembly into the vise of the mill, lined it up, and then we were ready to test. Pretty much we just turned it on, fed it in until it touched, and then we let it heat up, and then we did the rest of the process. There's a video on our poster, you can scan it, and you can watch our first test. We tested 16 times, we made 11 total samples, and recorded the time temperature for each. I'll hand it off to Jacob to talk about the results.
We had, like Dylan just said, we had 16 total tests. Of those 16, we were able to produce 11 samples. 8 samples were of the aluminum 1000 series round stock, which is shown right here. And then 3 were from the chips, which is, that picture on the left is the final product of that. And this one right here in the middle is a 3/8 probe round stock test as well. So once we had the samples made, we sectioned the 1/4 ones, which were the first ones we produced, and we put them in an epoxy resin as shown here, and we took it to a grinder and we polished the grains down, or the surface of the samples down, in order to be able to properly observe the grain structure. So then we took our samples in the epoxy resin, all polished up, to the LSU Shared Instrument Facility in Baton Rouge to be analyzed for SEM, or to prepare it for SEM analysis. However, due to the epoxy resin used and just the non-conductivity of the aluminum that we use as our base workpiece, it came out blurry, and so the electron microscope was unable to properly find the grain structure. So that provided some interesting problems for us. So we left some of these samples on the left without the resin. We left them there to potentially have them ion beam test them to see if we can observe the grain structure in any way. Here we have some of our thermal result data tests from our thermocouples. Like Dylan said, they're not exactly on the insert, so this is the exact temperature that the workpiece is experiencing during the test. Here on the right side are the 1/4 diameter tests, and on the left are the 3/8. It's seen through a general trend here that the 850 RPM tests in the blue, or in the purple and red, are occurring. The extrusion occurs at a faster rate than the 1000 RPM due to the higher torque from the machine. Some observations that we incurred are that the cost effectiveness of our project is extremely paramount in terms of just our budget. We had a $500 budget, and we were able to produce these for less than $400. $70 went to the poster that you'll see outside. So this is a cheap process as long as you have a mill. We use a 2 horsepower mill to produce these samples, while general extrusion processes require giant dies and massive amounts of force and pressure to produce wire or other extruded methods or materials. Here, the second point, higher horsepower mill and CNC will give us more consistent results, meaning that we couldn't measure the feed rate, we couldn't measure the exact amount of torque being placed on the workpiece during each test because it was just not possible for us. So we were literally standing there holding the cool feed lever, and however we were feeling for the day, that's pretty much the test results. And that's why there's differences in the data for the temperature. Some of the size of our dies will help us produce larger samples if we wanted that. If say we wanted to make giant chips, we would simply need to have larger chips or a larger die to produce a larger sample. And so that's kind of the effectiveness of this design. So what's the point of all this? What's our end goal for our samples? What do we want to get out? What do we want to see? We want to hopefully be able to produce new or better materials for the aerospace, automotive, biomedical, and oil field industries. Currently, this aluminum has better material properties than just a stock aluminum at the end of the workpiece. So with those things in mind, that's kind of what we were trying to get, the goal that we were trying to accomplish. And then also, as far as the chips go, our chip tests, there's a potential for recycling aluminum chips from manufacturing methods, such as just putting it on a lathe or on a mill. You can sweep those up, clean them, and re-put them in a die, heat it up, and then have a wire or a billet come out of it. So that's much more efficient than just having to melt them down, put them in a furnace, put them in a tray, and like just wait for it to cool off in a giant puddle. So some future possibilities for research that could be happening here or around the world. You could apply the design to a wide range of machines. We designed this in mind to put it on the lathe. However, we didn't get to that point in the semester. We just simply said, okay, the mill's more than effective to do this. We were worried initially about the length of the wires, and then after we ran our first test, we pretty much saw that it was no problem just putting it on the manual mill here at UL. So you'll be able to put it on a CNC, you'll be able to put it on a lathe, you'll be able to put it on its own special machine if that's what you wanted to. The correlation between the speed rate, feed, extrusion ratios, temperature, you're going to need a CNC machine. Here at UL, we weren't allowed to touch it per se yet, so hopefully with the proof that this process works, they'll allow us to work on the CNC or in the future. Next, the grain size and material properties. We didn't get to analyze the grain structure, as I said. The SEM results did not come out as we planned, so Dr. Ellen will take them over the summer and hope for optical microscopy will be able to prove some results in that aspect. And then, again, further chip testing. Here are our chips that we tested with, and that's one of the outputs that we made, and that's the output we made yesterday. The difference between these two tests, the far left piece is a spacer, a simple stock aluminum, and right there is a tube, and then this is a wire. So this is the second thing is hollow. The difference between the two tests, we used about double the amount of chips on this test than that, and they both came out of the probe after the process was over. With that, I'd like to end it. Any questions?